Rob Nelson. How you doing?
Good to see you. Thanks for coming by.
I'm trying to figure out how these earthquakes work. It sounds like you're doing some really interesting research. Can you fill me in on what we're learning about earthquakes from this? I mean, what is this?
So this is a machine where we actually make small earthquakes here in the lab. The earthquakes are about magnitude -2. It's very small. However, the physics of what's going on here is really no different than a large earthquake. The information that this machine generates is helpful to other scientists who simulate and model earthquakes, who want to get the best models possible.
And so this looks like a big chunk of granite or something, or marble. What is this?
So what we have, the samples here, it's a Sierra white granite. Granite is very representative of the Earth's crust, so if you're gonna do earthquake simulations and you want it just a very representative rock, granite's a good choice for that.
In San Francisco, you've got the Pacific plate and you got the North American plate, and they're side by side and they're like slipping past each other. And that kind of friction that builds up and then is released is what causes an earthquake. And so you kind of have the same thing going on here, right?
Right. The diagonal here is our Strikeslip Fault. It's 2 meters long and about 0.4 meters deep. It's instrumented with devices that measure slip at many places along the fault.
So even on this little tiny piece of block, when you have a slip, you can measure a difference from one end to the other. It's not all slipping at the same time.
That's right.
Can we run a simulation?
So I'm going to start that program now.
So right now you're pressing the two blocks together and are like putting strain on it.
That's right. So the blocks are being pushed together this way. That's the normal force pushing the fault together. And I'm also applying a shear force that's trying to slide the blocks past one another. Eventually the shear force will get close to the strength of the fault and eventually will exceed that.
We're simulating an earthquake right here. We've got two big blocks right next to each other, because like an earthquake, you don't know when it's gonna go off. I don't know why I'm getting nervous, Brian.
I can see on my sensors up here that these are measuring fault slip and they're actually changing pretty quick. And here, this is curving down.
It's gonna happen any second now, guys.
We should have an earthquake shortly. There we go.
Oh, geez. Woo!
There's the earthquake.
That was intense. So when that earthquake went off, what were we able to tell? I mean,
so
you've got all these sensors.
From this, I can tell that we had the accelerating fault creep, so we could see the nucleation process. There's our stress drop right there, the difference between there and there.
Okay.
So there's a variety of things that we can tell just from these two curves. And that's the information that is most helpful to study earthquake hazard, really.
My heart's still beating from that earthquake. Oh my gosh. Thanks.